Okay, our topic here is flow kinetic energy. How can we understand the physical processes that are driving a flow by looking at the evolution of its kinetic energy? We'll start here with Cauchy's equation, which we derived previously. It tells us that rho times the material derivative of the ith component of velocity, let's get this up here, is equal to the gravitational force, rho gi, and then the surface force from the stress of surrounding molecules, okay, which is the divergence of the stress tensor, di by xj, tau ij. Now, to get an equation for the kinetic energy, we're going to dot this with the velocity vector itself. So we'll have ui rho dui by dt equals rho ui g plus ui d by dxj of tau ij. Okay, and we're going to number these terms, 1, 2, and 3. What we'll do is we'll take each of these terms and do a few simple manipulations on it to tell us a little bit about what it means, and then we're going to integrate each term over a material volume that will represent a fluid parcel, and from that we'll get a much stronger insight into the physical meaning of each term. So first, let's work with term number 1. So term number 1 looks like this right here. It's ui d by dt of ui. Now, the material derivative, big D by dt, is just a sequence of first derivatives, and so we can bring ui inside the derivative just the way you would with any other derivative, and write rho d by dt of ui squared over 2. And you recognize that this is very similar to the kinetic energy. It's the mass per unit volume here times d by dt of the square of the velocity divided by 2. Okay, how about the next two terms? Well, term 2 is really trivial. It's just the dot product of u with the gravitational vector. Term 3 we can do something useful with. It's ui d by dxj of the stress tensor, and we can write that by taking the ui inside the derivative as d by dx j ui tau ij. But we have to pay a price here. We have to subtract off something else, which is dui by dx j tau ij. And if you don't understand why that is, recognize that we're just using the product rule sort of in reverse here. If a b primed is a prime b minus b prime a, oops, that's not minus, it's plus, a prime b plus b prime a, then we can rewrite that as, say, a b prime equals a b all primed minus b a prime. And that's what we've used here, where our a is u and our b is the stress tensor. Now, before we continue, it's worth doing a little bit of extra work on the final term here, dui by dxj tau ij. Let's see. Remember, dui by dxj is just the velocity gradient tensor, which can be expanded out as the strain tensor eij plus a half Rij, the rotation tensor, multiplying tau ij. And we know that because the rotation tensor is antisymmetric and the stress tensor is symmetric, then their product is 0. You just proved that in a homework. Just a little bit. Okay, and so what this term really adds up to is just E ij tau ij, the strain times the stress. So gathering everything up, we've got a kinetic energy equation. It says the density times material derivative of ui squared over 2 is equal to the gravity term and then this gradient term minus strain times stress. And we're going to label those terms 1, 2, 3, and 4. And now we're going to take each one and integrate it over some material volume. So we'll apply this operation to it, the integral over a material volume of the term times dV. We'll do that one term at a time, starting with term number 1. Remember that when you integrate rho times d by dt of something over a material volume, we already got this from the Leibniz rule. We get d by dt of the integral over the material volume of rho times whatever it was, in this case ui squared over 2 dV. And this is a very good thing because we now have the kinetic energy of the fluid parcel, the integral of the mass per unit volume times kinetic energy per unit mass, u squared over 2, integrated over the volume. So we've got the material derivative of the kinetic energy of our volume. The next term is very simple. It's just the integral of the gravity term, rho ui gi, over the volume. Now, we're left with terms 3 and 4, and we'll work with term 3 for a minute here. When we apply the integral over the material volume Vm of d by dxj ui tau ij, we recognize that we're just taking the volume integral of the divergence of something, because I is a dummy variable, and ui tau ij then is just a vector whose free index is j, and so this is d by dxj of something j. This is the divergence of this vector here. And using the divergence theorem then, we can write the result as the integral over the surface of our fluid parcel, which we'll call am, of ui times the outward normal to the surface, n, oops, that should have been a j, nj tau ij, integrated over the area, and recognize that nj tau ij is just equal to the ith component of the force per unit area, Fi. Okay, so we're finally left with the integral over the surface of am ui Fi dA, which is just, you should recognize this from our discussion of the solid body. This is just the rate of working, velocity times force, by the force per unit area acting on the surface of our fluid parcel. And how about term 4? Term 4 is negative tau e, so minus the stress times the strain. Now we're going to make an assumption. Let's assume that we have a Newtonian fluid. assume Newtonian. Then we can substitute the Newtonian expression for the stress into here. So the stress is minus pressure times delta Ij plus the second viscosity lambda times EKK delta Ij. And remember, EKK is just the divergence of U. It's this trace of the strain tensor, or the divergence of the velocity field. And then plus 2 mu Eij, and then the whole works gets multiplied by Eij. Okay, let's look at these terms individually, just as we have been doing. We're going to separate them up into term 1, term 2, and term 3. Term 1 we'll look at first. It's just the pressure times the delta times Eij, and that's easy to work out. The minus signs cancel. We have the pressure times, say, EII, sum over the dummy index j. Okay? So pressure times divergence. This is called the expansion work. If the fluid is expanding in our fluid parcel, then the pressure within the fluid parcel supports that expansion and causes it to do work and increase the kinetic energy of the motion. Now, how about term 2? Term 2 we can treat in the same way. It's got the minus sign. It's got the minus sign, and we have EKK. Forgot the lambda. Just a second. Let's go back. Go back a little bit. We'll have minus lambda EKK, and then multiplying delta by Eij again, we get EII. And notice that what this is minus lambda times the square of the divergence. This is a negative definite quantity. It means that there's a loss of kinetic energy. Okay, for comparison, consider the expansion work can be positive or negative depending whether the fluid is expanding or contracting, whereas the second viscosity has the effect of being negative in either case, for expansion or contraction, because of this square here. So second viscosity means the fluid doesn't like to expand and it doesn't like to contract. Either way, second viscosity is going to remove kinetic energy from that motion. Okay, then finally we've got term 3, which is a pretty interesting process. Term 3 gives us 2 mu Eij Eij, and it has a minus sign. So this is also a loss, and this is the loss due to dynamic viscosity. We often write this in terms of a quantity epsilon. We write it as minus rho times epsilon, and I'll show you what epsilon is here. Epsilon is given by epsilon equals 2 mu over rho Eij Eij. Epsilon is the dissipation rate of kinetic energy. It's the rate at which kinetic energy dissipates due to viscosity. Okay, and notice that it's positive definite, because Eij Eij just means we're taking each term of the strain tensor, squaring it, and then adding them all up. So this is the kinetic energy dissipation rate. It's also useful to define another quantity here, the ratio mu over rho, viscosity over density is often called the kinematic viscosity. The kinematic viscosity, and symbolized as nu, the Greek letter nu. And so we end up with epsilon equal to 2 nu E I J E I J. Collecting everything up, we now have a big complicated equation. It tells us that d by dt of the kinetic energy of a fluid parcel is equal to a bunch of different processes. One of them is the action of gravity, which we'll say more about in a minute. The second is the rate of working due to surface forces. So this is forces exerted by the surrounding fluid at the surface of our fluid parcel. The third one is the expansion work, the pressure supporting the expansion of the fluid and adding to its kinetic energy. The third is the loss due to second viscosity. It doesn't like the flow to either expand or contract, and if it does, it removes some kinetic energy. And the third is the loss due to regular friction. It's called the dissipation of kinetic energy. Now, before we finish, let's look one more time at the gravity term. So the gravity term is the integral of density times the dot product UIGI. Now, we're going to do something I don't like to do very often. We're going to cite results for a particular coordinate frame. We're going to represent this in a gravity-aligned coordinate frame so that the gravity vector can be written as minus g e hat z. Okay, so g is the regular gravitational acceleration, 9.81 meters per second squared if you're at the Earth's surface, and E hat z is the vertical unit vector, and it has to be aligned with gravity. It can't just be any old thing that you choose to label as z vector. Okay, you get the idea. So in this case, gi is minus g delta I 3. It's only non-zero if I is 3, and therefore rho ui gi is minus rho g w, w being the 3 component of the velocity vector u. Now, there's another thing we can recognize about W. W is equal to d by dt of the vertical coordinate z. Okay, W is just the derivative following the motion of a parcel of the parcel's height. And if you don't believe me, just write down dz by dt and expand it out in all its glory. It's partial dz by dt plus u partial dz by dx plus v partial dz by dy plus w partial dz by dz. And notice that most of these terms are 0. Z doesn't depend explicitly on time. It's an independent coordinate. Similarly, x and z are independent of each other, and y and z are independent of each other, but dz by dz is equal to 1. So mathematically you get that dz by dz is w. Now when we integrate this term over the volume now, we can just replace the integrand with rho big D by dt of gz. And all I've done here is bring the g inside the integral, which is inside the material derivative, which is easy because it's just a constant. And now we are once again in that nice situation of wanting to take a volume integral of rho times something, and using the Leibniz rule in combination with mass conservation, we can write this as d by dt of the integral over our fluid parcel of, guess what, rho g z dv. And look what we have here. We've got the potential energy of our fluid parcel, right? It's just potential energy of a solid object is mass per unit, no, mass GH, and now we've got mass per unit volume, G, height, integrated over the volume. So this is nothing but potential energy. Now, I forgot, these are supposed to all have minus signs attached to them when we go to substitute into the equation. So everything here is negative, and now when we substitute this back into the original equation, our potential energy term can be brought over to the left-hand side, and what we have is just d by dt of kinetic energy plus potential energy. So we have Ke plus Pe is equal to the contributions from all these different processes, the rate of working by forces from external molecules acting on the boundary of the parcel, the expansion work, the work due to the second viscosity lambda, and finally dissipation due to friction. And one final thing I'll point out is that the dissipation due to friction sends energy off to another form of energy, which is heat. So it converts kinetic energy into heat, and we'll deal with the implications of that next.